So in question 28, we're given that a reflecting surface is covered with a thin film of refractive index n and thickness t, and we're given that the refractive index of the reflecting surface is much greater than the refractive index of the thin film. And we're asked to find the minimum thickness of the film so that no light is reflected back into the air. So what happens here is that this light is incident on this boundary, and since the refractive index of the thin film is larger than that of the air, there will be a phase shift over here of pi. So when it gets reflected, it gets shifted by pi. So when it reflects back, and the rest of the wave will continue traveling in here. And here as well, the refractive index of the surface is larger than that of the thin film, and therefore is also going to absorb is also going to have a phase shift of pi when it gets reflected back. So in result, the waves that will meet over here, so this wave and the reflected wave from here, compared to each other, they will have no phase difference, which means that this will have to be a destructive interference, as we don't want any reflection. So the way we can have no reflection is that if both of these reflections cancel out when they come back in the air. And so for that, the condition is that their wavelengths have to be a odd number apart from each other. So we will have to use the equation 2dn is equal to m plus a half lambda. This is for destructive interference. So we want the smallest one, so we'll just say m is 0. So we can say that 2dn is equal to 1/2 lambda, and then d is what we want. It will simply be 1/2 lambda over 4n, which is option A.